In this problem, we've got a parallel plate capacitor with a given spacing between the plates and an electric field strength. So I've drawn this here. So let's take a look. And what we're asked to do is we're going to place a proton at the positive plate. Okay, so this is a proton. Okay. And so what's going to happen there is it's got an initial velocity of 0. However, it's going to be repelled by the positive plate and attracted to the negative plate. So there's going to be a force that brings it to the other side. And so there'll be some, oh, did not intend a triangle. So there's going to be some final velocity here. All right. I'm also going to draw for reference the fact that we do have an electric field, and that electric field is going to be from the positive to the negative. And in between the plates, the electric field is going to be constant throughout. I'm just going to draw out a few representative field lines, remembering that the electric field is by convention directed such that a positive test charge would feel a force. And because this is a constant electric field, if we were to place a positive test charge on a field line, this would also be its trajectory. And so we see that in the case of the proton, where it would effectively follow a field line had I drawn one at that location. Okay, so let's get into quantitatively assessing what's going on. And this is in fact very similar to questions that use gravity to convert gravitational potential energy into kinetic. This is very similar to dropping a ball. So what's really going on here is that we have some potential energy in this system, some electric potential energy, and that's going to be converted to kinetic energy, which is the motion of the proton. So let's take a look at each form of energy altogether, because what we really are doing is a conservation of energy question. Because energy in this system will be conserved. So the change in the potential energy plus the change in the kinetic energy is 0. Well, let's take a look at each form of energy in this system. So we have a potential energy of the proton, and so the change here is going to be the final potential energy minus the initial potential energy. This is electric potential energy. The final is 0 because it's resting up against the negative plate. And then the initial potential energy is QED, where D is the distance between those two plates. Okay, so the change in the potential energy of the proton is negative QED. Let's look now at the kinetic energy of the system. Well, our change in the kinetic energy, which I'll denote as capital K, is the final kinetic energy minus the initial. So these are both going to be terms 1/2 mass of the proton velocity squared. I'm just going to leave it as velocity F because there's only one object moving, and the initial kinetic energy is 0. So our change in the kinetic energy is 1/2 mass of the proton Vf squared. I'm just going to separate this out a little bit. Okay, So now we can go back down to our conservation of energy statement, and we can substitute in some values. So we have negative QED for our change in the potential energy, and then we've got 1/2 mv squared for our change in our kinetic. And now it's a matter of rearranging and isolating for the value that we want, which is this final velocity. So first, we bring over the QED term, and then I'm going to bring up the 2 and divide this through by mass of the proton, and we're going to get rid of the square. So there we go. And what we need to do now is substitute in some values. So our Q term, so we've got 2, and then Q is the charge on the proton, which is positive E, our fundamental charge, or 1.6 times 10 to the negative 19 coulombs. Our electric field was given to us, and that was 50,000 newtons per coulomb. And then our distance was 2 millimeters, or 0.0020 meters. And this is all over the mass of the proton, which is 1.67 times 10 to the negative 27 kilograms. Okay. So if you substitute all that, you know what? It looks a little crowded. So I'm going to move this down here. Get a little bit more room. Don't want to, there's no need to make this all scrunched up. Okay. So 0.0020 meters. And we had square root sign over all of this. Okay. See that a little easier, and so we can say the final velocity works out to 1.4 times 10 to the 5 meters per second. Okay, and that's it. So this really was a conservation of energy question dealing with the conversion of electric potential energy to kinetic energy. And this was very similar in form to if you were to take a ball, hold it at a height, and drop it. And so it would have converted potential to kinetic in the same way.